All of your design work and careful construction of the database lead up to this point where you begin to fashion information out of the raw data that you've collected. Structured query language, or SQL or SQL, however you want to pronounce it, is the lingua franca of the database world. It can be used to build a database. It can be used to edit, to update, to modify, to delete. And in the form we're going to see it today, we're going to see how to query using SQL. For us, in this series of primers that we've gone through from the design process up to now, SQL represents the other end of the design process where all of our preceding work is finally going to pay off and we're going to get some information. Our objective is to produce information from the raw data that we've built into the database. So if we've done everything correctly, if we have built our database according to the proper standards, we can expect to have absolutely complete confidence in the results that are returned from any SQL query that we pose to the database. In other words, if we query the database and it returns 0 rows, we can be absolutely sure that no data that meets our criteria exists in the database. If it returns a single row, we can be absolutely sure that that was the only set of data that met our criteria. Every command that we put together in SQL has a required syntax and a required order to that syntax. The control language in itself is very simple, and you can do a lot of things with it. You can as we've said, you can construct the database, you can modify the contents, you can delete and add rows, and what we're going to focus on today is, of course, building queries with this. So when we go to develop an SQL query, it's composed of 3 clauses: the select, the from, and the where. Each of these is important in its own way. The select and from are required components, and the where clause, we can add that on later if we want to be more specific in what we're trying to extract from the table. So let's look at each one of these. The select clause specifies the columns, the fields, the attributes, whichever term you want to use, that are going to be returned in the result set. So for example, if we're going to choose the first name and last name of our employees, we're going to say select last name, comma, first name, and then specify the table from which those results are coming. There are also field types that can be constructed through the execution of the query. For example, we can use sum, and we'll see that in the example. We say sum on a specific field, and it's going to add up all the numbers that we list according to the rest of the specification. So select defines the columns that are going to be returned. We must also specify the source using the from clause. The source says, get those columns from this or these tables. Without this, there's no way for the SQL interpreter to understand what tables to get the columns from. So we're always going to say select certain fields, or all the fields, whichever way we go, from this table or these tables if we end up creating a join. And finally, the where clause is the optional component of this statement. Where specifies the criteria by which the rows are going to be selected. So for example, we say select first name, comma, last name from employee, where employee last name is Rachele, or whatever criteria we want to use. That criteria can be multifaceted. We could say, for example, where last name equals Smith and first name equals John and date of employment is greater than December 5th, 2013. Whatever way we want to look at that, we can stack these things up in the criteria. There are other optional parts of the complete SQL clause, but when we put them all together in their simplest form, we get something like this. So select first name, last name from employee, where employee birthday equals today. So it's going to evaluate each employee in the table of employees and look at the field called birthday. If birthday is equal to today's date, whatever today's date is, we send them a Christmas card or a cupcake or something over their desk. Okay, so this creating a query is pretty simple, but that simplicity kind of disguises how powerful this function really is. When we look and try to put things together, when we create the query, the last thing we want to keep in mind is that it creates a new table. The results set is a new table, and conceivably, if you do things right, you could save that new table and run additional queries against it. So this is not something that runs and then disappears. It can be something that runs, creates a subtable, and then we can do further operations on this table. So in our next bit, we're going to look at some examples of how all this stuff comes together. As we look at some SQL query examples, we want to first look at the database that we're going to use for these test purposes. It's very simple. It's composed of 4 relations, 4 separate tables. The assignment table contains the employee who is assigned to what project and the number of hours that they have put in on that project. Our department information contains location and telephone data. Our employee field, probably the most important, contains our first and last names, department that employee is assigned to, and their contact information. And finally, the project table contains the projects that we have already completed or that we are still working on. So all of those will be interconnected as we look at these different examples. Our first SQL query is really very simple. It specifies the columns that are to be returned using the select clause, and it says from where those columns are to be drawn using the from clause. So it says select, project name, department, max hours. These are all fields or columns from within the table, project. So when we execute this, it runs quite nicely and it returns exactly what we asked for. So a very simple query specifying the different columns to be returned and the table that produces the source data. Here's another simple query. In this case, we are going to, when this is executed, return one single column, department, from projects. Now when we run this, we see something that might or might not be a problem depending on what we're looking for in the output. Notice that marketing appears here, and then marketing appears down here. Finance here, finance here. We can modify this query by putting a simple modifier in on the statement so that when we execute it, it only produces unique information. So if we add the modifying syntax distinct to this example and run it, you see that it does away with the duplicate data. So if your query requires that you bring back a column that contains duplicate data, which is okay as long as the whole row is not duplicated. And you just want to see the components of that table. Adding the distinct modifier will only show the first instance of each one of those, in this case, departments that's displayed up here. In our third example, we are a little bit more complex because we're adding a where clause. And this where clause, if you remember, specifies the criteria that will determine which rows are returned. So we're going to say select project ID, name, department, hours, start and end dates from the project field, but only return those rows where the department, that particular field, is equal to finance. So when we execute this, we see that it limits the rows returned to only those equal to finance. Your where clause is an extremely powerful component of your SQL queries. Your where clause can stack up a number of criteria. It can give a range of criteria that you want to look at. It can say specific fields that only reach a certain limit. In fact, let's look at a query that does just that. As we look at this, you see that number one, we've changed the selection choices to a wildcard. So as soon as I put that asterisk in, it says select all of the fields, every single field from project. In this case, the where clause is modified a little bit, and it says where the maximum hours allotted is greater than 135. And so when we run this, we see that it returns only those projects where more than 135 hours have been allotted for the completion of the project. If we, let's say, wanted to drill down a little bit, so we'll see we have three separate departments involved in projects here. And perhaps I'm only interested in the projects where the finance department is involved and they've allotted X number of hours. So I can modify this query and I can add the modifier and. So it says this criteria, max hours greater than 135, and department equals finance. Now it says that both, as soon as I put the and operator in there, both of these criteria have to be true in order for a row to be returned. So as I execute this, you see that it has now narrowed this down. I've drilled down into a specific field. So the and modifier, we also have an or modifier. So if this is true or this is true, then return that specific result. Now this is an example of the OR operator. So select first name, last name from the employee table where the department equals accounting or a specific telephone number, a specific departmental phone number is included. And so as we execute this, you see that we got our two accountants, Tom Carruthers and Heather Jones. They were returned because it was equal to accounting, and it has returned the name Mary Abernathy because her telephone number was put in as a part of the criteria. So you're beginning to see, just as we build these very simple queries, that there is a lot of power invoked within the where clause. Now this example is similar. We're going to select things that reach a certain criteria, but what I've created here is a range of criteria. What this query essentially says is show me the last name, the telephone number, and department of all employees who work for accounting, finance, or marketing. So anything within this range of values is going to be returned. And so as I execute it, you see I get accounting, finance, and marketing return back. So now by making these simple modifications to the same SQL syntax, we find that we're just vastly expanding the power of each one of these queries. We can negate this range as well. We can use the negation operator, which is not, and place that in the query and execute it. And now we see everybody who is not within that range. You see that it has not returned anybody in accounting, finance, or marketing. It has given us everybody outside of that criteria. As we look at this next example, we've done something similar, but we've done something more specific at the same time. We're going to use the between operator so that it looks at a specific value between this and this. The other one said anything in this range, and it really didn't have a stopping or an ending point. This is a different kind of a range. It is in this case, numeric range between 2 and 5. So if we execute this, we only get employees whose numbers fall between number 2 and number 5. And in all these cases, you can always go back and you can examine your results against your table. As you're developing the query, as you're testing it out, you say, I want to see, did I get 2 through 5? And so we see we start with Rosalie Jackson and we come down to Heather Jones. And so if we go and we examine our the rows that were returned back, we see that we got exactly what we asked for. Again, demonstrating the great benefit of the relational system. I know that there is no duplicate data contained in this database. I know that if it exists, the data that is returned here, the information that is produced through these queries, is going to be precisely what it is I'm looking for. Now, this is a little bit different here. And you may see this in a couple of different forms. I'm going to have to modify this, but I wanted to show you the normal SQL form. We recognize the first wildcard character, the asterisk, and that says select all of the fields from employee. Now, the where clause looks a little bit different. Where the phone is like, and then we see a string of characters here. This would say anything that is like 360 and a dash in that position, 287 and a dash in that position. And in most normal SQL interpreters, these are 4 underline characters. So 1, 2, 3, 4. The underline says show me a character that fits in this. So anybody really that has the 287 prefix should be returned. Now in Access, we've got to do this a little bit differently. We're going to delete this and put pound signs in there. And when we execute it, we see that we get everybody with a 287 prefix. So if your data is a little bit fuzzy, if what you're looking for seems a little bit fuzzy, then you may want to use these kinds of substitutionary wildcard characters that allows you to ask a relatively fuzzy query. In other words, you don't have to specify the exact characters you're looking for. Again, you're looking for something that is roughly similar to what you've asked for, and that's the result that we got here. In our final simple SQL example, we see that when we get these rows returned back, right now as we have looked at the output, we've seen that the result set is ordered in the order that they came out of the from table. So whatever order the employees were in, that's the order that they are displayed. In this case, I've added the modifier from employee. So I'm going to ask for the first name, the last name, and the department from the employee table. And then I give it the order by clause. The order by clause says sort these rows by department. And so as we execute this, we get exactly what we asked for. We get accounting, administration, finance, and on down the road. Not matching the original order of the tables, but matching what it is that that we'd like to see the tables in. We could have just as easily said order this by last name. In fact, let's just go ahead and modify that so that we get our table in alphabetical order. And we'll run that, and you see that now on down there. Again, you can stack these clauses up. You can order it by department and then last name within the department if that's going to be helpful to you. With 10 or 12 employees here, it wouldn't be very effective. Those examples that we just looked at all came from a single table. But many times we want to produce a query that will extract data from more than one table. The relational operation that queries two tables with a common attribute or a common field between them is called a join. SQL specifies a join in a command in the where clause. That is, the where this equals that, this is greater than that, whatever that is. It's done by specifying a common field that contains data in this table and contains common data in the other table, and that's what performs the join. We've talked about that in design terms as a relationship. This is related to that, and they're related on that common attribute, on that common field. As an example, if we were to draw an example, if we have a patient and a visit, each table, the patient table, the visit table, would have the patient identification number, the MPI number or the MRN, whatever we're using, as a column. So in each one we would find that same data. The query then says where patient MPI equals visit MPI. And as long as those two equal, we return back data that is joined together. When the join is made on the equality of data in those two common columns, this kind of a join is known as a natural join, or in other contexts, an equijoin. When there is when we use that terminology, depending on the context, that is the database tool that you're using, there might be a small distinction. Access doesn't recognize the distinction, but others will. The equijoin returns both common columns. That is, I would see MPI from the patient table as well as the MPI from the visit table. In a natural join, that would just return a single column, whichever one we specify from between those two tables. An outer join is one that returns rows that don't have matching columns. You know, it might be important, for example, to determine how many patients have registered but have not yet been admitted. So we would do an outer join that examines the admit or even the discharge date to see if maybe they're still in-house. The outer join would enable us to see the contents of the visit table where perhaps even the MPI number hasn't been added. So we pre-registered a patient, but they've never actually had the visit. And that happens quite a bit. So let's go back to the editor and look at some examples of a join. A join in an SQL query It's a little bit different animal, but much more useful, because now when we join tables, we can draw specific data elements or specific columns from multiple tables. So here's our very first simple example. Select first name, last name, and hours worked from the employee table and the assignment table. And then in our where clause, we essentially create the relationship between the two tables, where the employee number is equal to the employee number that exists in the assignment table. So that is setting up that relationship between the two tables, and as it executes, it will go through and it will find all of the employees that have a relationship between the two tables, and then return the specific data that we've looked for. And again, we could go back and verify that this join work by pencil or by desk checking against our existing database to make sure that that worked. So a join now is where we're going to draw data from more than one table. We're going to ask questions based upon common fields in the two tables. So we are going to, in this case, rely upon the employee number that exists in both of employee and assignment tables. And then using that, we're going to then join the two tables together in the output. So we get the full range of modifiers. In this case, we're going to use group by. Now this one's going to do something a little bit differently. When we ran that first query, let's just jump back there. When we run this query, you see that we get the hours worked for each of the employees involved with different projects. Now, that's not terribly helpful, because I'm going to have to go in, for example, on Mary Jacobs. I'm going to have to find her here, Mary Jacobs here, Mary Jacobs here, and add all those up. But why do that when I can build it into my query? So I'm going to use an SQL function called sum, and then I'm going to use that to total together the hours worked. So you see my query is a little bit different. I'm going to select first name, last name, and then sum the hours worked for each of these employees, and then return that as a new field called total hours worked. In my from clause, I also use a little shorthand here because it takes a long time to type employee out all the time. So I'm going to say employee as E. So I've assigned the alias E to the table employee, and the alias A as the employee to, or as the alias to assignment. So A and E are going to be employee and assignment, where E dot and then the field, and equals A dot and the field from within A, within assignment. And then I'm finally going to say group these, which gives me the total of sum, group on the employee by last name and first name. So when I execute this, you see what it does for me here. So now Mary Jacobs, instead of having to go and manually add that up, even though it was just 3 rows, it could have been 300 rows. So Mary Jacobs total 90 hours. Tom Jackson total 72.5 hours. So this has grouped all of the employee data together and then summed those hours and returned it back as a new field. So I've done a couple of things here. I've gone and I've done a join basically on the employee number, and then within that join I have used some of the SQL function to total those hours together, giving me a total now instead of making me go and have to pull that total together. In our last join example, you see that we do a left join. Now, there are left and right joins, and outer joins are a little bit beyond us just at this point, but what an outer join is, it specifies which side of the from clause we're leaning on. And the result is, again, very similar to what we've been looking at. You see that we get all the projects that are involved, the employees involved in each of the project, and the number of hours put together. If we wanted to drill down on this, we could go and group this together so we get all the hours worked. If we wanted to ignore the employees, all the total hours worked on the third quarter product plan, for example, and do that same thing down there. Or again, take the number of employees, identify them with a specific project, and group it that way. Lots and lots and lots of flexibility in the SQL queries. All of your design work and careful construction of the database lead up to this point where you begin to fashion information out of the raw data that you've collected. The design of the relational database system is oriented around that objective and the integrity of the information that's produced. If you have sound design of your relations, if you have carefully applied the database rules and the proper formation of your queries, all of that together equals one thing: absolute confidence in the results that you produce. Good luck with your database work, and we'll catch up again down the road.